Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Binomial lecture 4. So we'll be talking about complex coefficient summation series in this lecture and also we'll be looking at the methods to find them. So we'll be using three methods. The first method would be method of integration or differentiation. The second method would be usage of variable upper index. The third method would be reverse summation. So let us start the lecture. So we have these two questions. Prove that C1 plus 2C2 plus 3C3 till NCN equals to n times 2 raised power n minus 1 and the second one is this one. Now let us start the first one with the method 1, that is method of differentiation. Now whenever I'm starting any of these questions, I'll be starting with 1 plus x raised power n, basically writing the expansion for this one. So that gives me C naught plus C1x plus C2x square plus C3 x cube plus C4 x4 till Cn x raised power n, right? Now I can, in the question, I can see that if I plug just x over here, x equals to 1 over here, then I'll be getting C0 plus C1 plus C2 plus C3. But that is not what we want. We want 2 in front of C2, right? That can happen if I differentiate this term. Then this 2 would come over here, and that would become 2C2x. This would become 3C3x square, right? Now if I try to differentiate it, what I'll be getting n times 1 plus x raised power n minus 1 equals to, this becomes 0, this becomes C1, this becomes 2C2x, 3C3x square plus 4C4 x cube till NCN x raised power n minus 1. And now if I plug in the value of x equals to 1, then I'll be getting n times 2 raised power n minus 1 equals to C1 plus 2C2 plus 3C3 plus 4C4 till NCN, right? Now this was our method 1 and that is the simplest of all in such series, right? Now let's look at the method 2. So method 2 is basically usage of variable upper index. Now let us try to write this series in the summation format. That would give me sigma r times CR, where r goes from 1 to n. So this is nothing but 1C1 plus 2C2 plus 3C3, 1C1 plus 2C2 plus 3C3 till NCN. This is what we have written over here, right? Now let's take this term and try to modify it. So we have r times CR is nothing but NCR. This becomes n factorial divided by n minus r factorial, right? So this would give me r times n factorial divided by n minus r factorial, and I'll write r factorial as r dot r minus 1 factorial. So this r and r gets cancelled. Now we are left with n factorial divided by n minus r factorial and r minus 1 factorial. But that doesn't make any sense because we need either NCR or we need NCR minus 1 or n minus 1 CR minus 1, right? We need either of that. Now I can see I can write this entire term as n minus 1 factorial by changing this into this, and by changing this into n minus 1 minus r minus 1 whole factorial multiplied by r minus 1 factorial. This is nothing but this only, n minus r minus 1, right? So if I take n minus 1 as capital N, so this looks like n times capital N, this is capital N minus r factorial dot r factorial. This is what we have written over here. Now I can write this as n times capital NCR. Capital N is actually n minus 1, so n times n minus 1 C r minus 1, right? So after the transformation, we have got this. Now let's write the summation once again. So we actually had r equals to 1 to r equals to n. We have got n over here extra, that is constant, and we are getting n minus 1 c r minus 1. Now if I plug the value of r equals to 1 over here, I'll be getting n minus 1 c0, n minus 1 c0 plus n minus 1 c1 till n minus 1 c n minus 1, right? Now we know that already. This is nothing but c1, the primitive format of c0 plus c1 plus c2 plus c3 with n equals to n minus 1 over here. So in the earlier case, we had C0 plus C1 plus C2 plus C3 till Cn, and that was 2 raised power n. We proved that. Over here, n was hidden, right? But here it's not n, it's n minus 1. So we'll be getting n times 2 raised power n minus 1. So this is the second method, which is not that very intuitive, but it is the most reliable method. Now let's look at the third method. So we have studied two methods. Let's look at the third method. So we have been given series C1 plus 2 C2 plus 3 C3. Let's write it out. C1 plus 2 C2 plus 3 C3 plus 4 C4 till NCN. And let's write 0 C0 over here. That is nothing but 0 only. So let's call it as S. Now what I'll do, I'll reverse the series and write it once again. So this would become NCN plus n minus 1 Cn minus 1 plus n minus 2 Cn minus 2 till 0 C0. If I add both of them, I'll be getting 2S equals to the Cn is nothing but C0 only, because NCR equals to NCn minus R. So this becomes n times C0 plus, if I add both of them, Cn minus 1 would nothing but n minus 1 Cn minus 1 would nothing but n minus 1 C1. So this would also become n minus 1 plus 1 times C1, right? Similarly, we'll get, you can see that summation is n only over here. I can write it as nc1 plus nc2 plus nc3 till ncn. This is n times cn. Okay, it's not ncn, it's not like that. Okay, this is n times c0 plus c1 plus c2 plus c3 till cn. So this is nothing but n times 2 raised power n. This is 2 raised power n, and this was equals to 2s. So s equals to n times 2 raised power n minus 1. 2 from here. Okay. So this is our method 3, to just reverse and add and use NCR equals to NCN minus R. Now let's try to solve the second series with the help of method 1. So we have been given C0 plus 3C1 plus 5C2 till 2n plus 1 Cn. Now our starting would be 1 plus x raised power n only, right? Now we know that this is C0 plus C1x plus C2x square plus C3x cube till Cn x raised power n. Now we want to have 2n plus 1. So the first thought should have been, okay, we can raise the power over here, we can make it 2n plus 1. But we have to realize that we are going till n only. So we cannot raise the power. That is not a condition for us. Now the second thing we can understand over here is the difference is 2. If this is 1, this is 3, this is 5. So we have got the differences 2. So we have to do something to make the differences 2. So the first thought that comes to mind is I can write 1 plus x square is per n. That would give me C0 plus C1 x square plus C2 x4 plus C3 x6 till Cn x is per 2n. Now I can actually differentiate this one and I'll be getting 2C1, 4C2, 6C3. But again, I'll be getting differences too, but I'm not getting 3 over here, 5 over here. We have to get 5. So what I can additionally do, I can multiply x over here, right? So if I multiply x over here, I'll be getting 1 plus x square raised power n equals to C0x plus C1x cube plus C2x raised power 5 plus C3x raised power 7 till Cn x raised power 2n plus 1. Now if you differentiate it, then definitely you will be able to see 3 coefficient over here, 5 coefficient over here, 7 coefficient over here, right? So, and after that you just have to plug the value of 1. So that is the method 1 for doing the second equation. Now let's look at the method 2 to solve the second summation. So again we have to write this in the sigma format. So we'll be writing 2r plus 1 sigma r equals to 0 to n 2r plus 1 multiplied by cr, right? This is what we have written. If I put r equals to 0 over here, I'll be getting 1 times c0. If I put r equals to 1 over here, I'll be getting second term, that is 3c1. Similarly, if I put r equals to n over here, I'll be getting 2n plus 1 times cn, that is the last term. Right? Now I can write this in two parts with the help of sigma properties. So I can write it as 2 times sigma r equals to 0 till n rcr plus sigma r equals to 0 till n cr. This we already know, that is c0 plus c1 plus c2 plus c3. So that is nothing but 2 raised power n only. And this we have already calculated. This one, this is nothing but this one only, but 2 times. So 2 times of rcr. This was nothing but rcr, sigma rcr, right? So this is 2 times n dot 2 raised power n minus 1 plus this. So this becomes n times 2 raised power n plus 2 raised power n. So this becomes n plus 1 2 raised power n. So this was our second method. So now since you have used this one to derive this one with the help of second method, you can actually remember this one, n dot 2 raised power n minus 1, and that would come in handy in solving the questions. Now you can take the third method, that is the reverse summation method, as the homework, because that is the easiest one. All you have to do, you have to write this one, and all you have to do is the reverse of this series and write this one, and again do the summation and do the calculations. That is the easiest one of all. Now let us look at this question. Prove that C0 plus C1 by 2 plus C2 by 3 plus till Cn by divided by n plus 1 equals to 2 raised by n plus 1 minus 1 divided by n plus 1. Right? Now, since we have done the derivative part, we can clearly see that we have n plus 1 over here. We have coefficients like 3, 2, basically 1 over here and 2 over here, 2 over here and 3 over here. So that gives me the feel of integration, right? So what I'll be doing, I'll be starting with 1 plus x raised power n equals to c0 plus c1x plus c2x square plus c3x cube till cnx raised power n. And then I'll be integrating it from 0 to 1. Okay. Why it's 0 to 1? Because we ultimately have to put the value of x equals to 1, right? If I'm integrating it, I'll be getting c1x square by 2. I'll be getting c2x cube by 3, right? So we are getting the coefficients, and to find out the series summation, we have to put x equals to 1. But in case of integration, we have to put the limits as well. So basically, I'll be integrating it from 0 to 1 and 0 to 1. So I'll be getting over here 1 plus x raised power n plus 1 divided by n plus 1, limits goes from 0 to 1, equals to, this becomes c0x plus c1x square by 2 plus c2x cube by 3 plus c4x raised power 5, sorry, plus c3x raised power 4 by 4 till cn x raised power n plus 1 divided by n plus 1, and limits goes from 0 to 1. If I plug the limits over here, I'll be getting 2 raised power n plus 1 divided by n plus 1 minus, I'll plug the 0 value over here, I'll be getting 1 raised power n plus 1 divided by n plus 1. This is equals to, if I put the value of 1 over here, I'll be getting c0 plus c1 by 2 plus c2 by 3 plus c3 by 4 till cn by n plus 1 minus 0 only, because if I plug the value of 0, the entire series would become 0, right? And now you can clearly see that this is the required answer. This is what we have written over here, and this was the summation which was asked, right? Now let's look at the method 2, that is the variable upper index method. So we have sigma r equals to 0 to r equals to n divided by r plus 1 cr. This is what we have written over here. If I plug r equals to 0, I'll be getting c0 by 1. If I plug r equals to 2, I'll be getting c1 divided by 2, right? This is what we have been asked. Now let's try to modify this expression. So cr is nothing but n factorial r factorial n minus r factorial, and also multiplied by r plus 1, right? Now I can club this r and r plus 1 into r plus 1 factorial. I'll be writing this as r plus 1 factorial. Now again, this is n plus 1 minus r plus 1 factorial. N minus r can be written as n plus 1 minus r plus 1 factorial, right? Now that gives me the hint that why don't I multiply and divide by n plus 1, and I'll be getting n plus 1 factorial in the numerator divided by r plus 1 factorial multiplied by n plus 1 minus r plus 1 whole factorial, right? Now this is 1 upon n plus 1 multiplied by n plus 1 c r plus 1. Now you just have to do the simple 2 raised power n plus 1 formula and you'll get the answer. Okay. Now let us talk about variable upper index. So we have used the concepts earlier basically while deriving the series summations, but we haven't formally derived anything out of it. So let's try to use those methods to derive one formula, that is NCR plus NCR plus 1 equals to n plus 1 CR plus 1. So let's try to derive it. NCR is written as n factorial C n minus r factorial in r factorial. Similarly, NCR plus 1 would be n factorial divided by n minus r minus 1 factorial and r plus 1 factorial. Now I can take n factorial as common and take the LCM. So over here we can see that this is, I can convert this into r plus 1 factorial by multiplying r plus 1 in the numerator and denominator both, right? We'll be getting r plus 1 divided by n minus r factorial and r plus 1 factorial, right? Plus over here I can convert this into n minus r factorial by multiplying n minus r in the numerator and denominator. So n minus r times n minus r factorial and r plus 1 factorial. Now I can write it further as n factorial. So r and r gets cancelled out. In the numerator we'll be getting n plus 1 divided by n minus. Now I can again write this as n plus 1 minus r plus 1 factorial multiplied by r plus 1 factorial. Why I did that? Because we have n plus 1 in the numerator. We have r plus 1 factorial in the denominator. So I have to write it in this manner only. N minus r can be written as n plus 1 minus r plus 1 factorial. Now this becomes n plus 1 factorial divided by n plus 1 minus r plus 1 factorial multiplied by r plus 1 factorial. So this becomes n plus 1 c r plus 1. So this is how you have to derive it. So very standard processes, basically you have to expand it, take the and do the adjustments. Okay. Now let's look at one example. Prove that ncn plus n1 n plus 1 cn plus n plus 2 cn plus n plus k cn equals to this. Now in the formula we studied that ncn plus nc n plus 1 equals to n plus 1 c n plus 1. But we don't see any number over here, any term over here where the two upper indices are common. So how to proceed with this one? Initially we might feel that okay, there must have been some misprint over here, but it's actually not. So basically we know that ncn is nothing but 1 only, right? So I can write this as n plus 1 cn plus 1 as well, because that would also make it 1 only. So this is 1 and this is also 1, and now I can see the terms collapsing. Right, now summation of these two would give me, this is nc1 n plus 1 cn plus 1 and this is n plus 1 cn. So that would give me n plus 2 cn plus 1, right? And now if I club both of them, I'll be getting n plus 3 cn plus 1. I can keep on doing that until I'll be getting n plus k plus 1 cn plus 1. So the main trick was over here only. Now let's look at this question. The value of 50C4 plus sigma this is. So let's try to open sigma. I'll be getting 50C4 plus this becomes, if I put r equals to 1 over here, I'll be getting 55C3 plus 54C3 plus 53C3 plus 52C3 until the end. The end term would be r equals to 6, that would be 50C3. So we have just one more term over here, 51C3 plus. Okay. Now it's written in the reverse manner. What I'll be doing, I'll be clubbing these two. So 50C4 and 50C3, that would give me 51C4, right? Now if I club 51C4 and 51C3, I'll be getting 52C4. Now I have to club it with this one. I'll be getting 53C4. With this one, we're getting 54C4. With this one, we'll be getting 55C4. And the last one would be this one, that would be 56C4. This is our answer. So these are the kind of basic problems you can get in the variable upper index formula. So today's lecture was till here only, and we have almost completed the binomial series. And tomorrow I think will be the last lecture of binomial. So let's meet tomorrow. Thanks for watching.